All right, my SM1 kids. This is it. This is the last section of the year. Y'all ready for this? I am. So, 11.4, congruence and transformations. Okay, you remember what congruence means, right? It means they're the same size and shape. And transformations is what we've been talking about this whole section. This whole chapter, I should say. Okay, so just a matter of really vocabulary. Two geometric figures are congruent figures if and only if there is a rigid motion or a composition of rigid motions, that means more than one, that maps one of the figures onto the other. Blah, 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 blah. I know, it's a lot. That's a lot of words. Okay, so in other words, congruent figures have the same size and shape. It doesn't matter how many times you move them around or flip them over or rotate them. It doesn't matter. As long as they're the same size and shape, they're congruent. Okay, so remember that translations, that's what we talked about, it's up and down, back and forth. Reflections, okay, like a mirror image, flipping back and forth. Okay, and rotations, okay, this motion, they're all rigid motions. Okay, so congruent shapes, look, these all have the same shape, even though they might be flip-flop. They still have the same shape. These are not congruent, as you can probably tell. Another way to think of it is if you take like a piece of, you have a shape, and you take a piece of paper and you cut it out the same shape, and you're able to lay that shape on the other one and it fits perfectly, that's congruent, even if you have to turn it over and do it that way. All right, so identifying congruent figures. So we just need to come over here and look at the ones that we have. All right, so if we look really close, well, you don't have to look that close. Look, this is a square. It has 4 squares on the inside, and so does this one. So these two are congruent. Okay, this one is a right triangle, and it's 3 units across, 2 units up. This one's also a right triangle with 3 units across, 2 units. So these two are congruent. And then we're just left with triangles that are 2 and 2. So 2 by 2, 2 by 2, okay? So those two are congruent. Pretty simple, I think. Okay, so congruence transformations. This is basically just vocabulary. Okay, but I am going to read this. It says, another name for a rigid motion or a combination of rigid motions is a congruence transformation. I don't know if you remember in a previous video I said that not all transformations are rigid. Okay, we have, like, say I've got a circle, and you can move that circle around and rotate it and everything else. But there's a transformation called a shrinking, and a stretching, and those are not congruent. But they are a different kind of transformation. Okay, so rigid motion is a congruence transformation because the pre-image and image are congruent. So this is kind of the important part. The terms rigid motion and congruence transformation are interchangeable. They're exactly the same thing. That's what they're talking about. Okay, so describing a congruence transformation or describing a rigid, what was that called again? A rigid motion. Okay, so what is it that's happening here? When we're going, how is ABCD mapping to EFGH? Well, we've got a couple of options. The one I think I'm going to do is, if I take this and I rotate it to this side, okay, this is a rotation. So the first thing I'm going to do, not a rotation, I'm sorry, a reflection. This is a reflection in the y-axis. You've probably also heard me say a reflection over the y-axis. So both of those are correct. Okay, so I've done that, and now how do I get from here to here? Well, that would be a translation and it would be, if I'm going from point to point, 1, 2, 3, 4 units down. Okay, so I thought maybe I had to try this for this one, but so that is how we would, this is a composition, it's two different motions, two different transformations. Okay, so reflections in parallel lines. All right, I promise this looks more complicated than it is, but there are some details of this that are important, so you may want to write some of this down in your own words. You don't have to write it down exactly the same, okay? So if lines K and M are parallel, okay, so we've got K and M, they're parallel. We know that by these little tiny arrows right here. Then a reflection in the line K, followed by a reflection in the line M, is the same as a translation. Okay, so we've taken this line segment and we reflected it over this line, and then we took that and reflected it again. That means basically we took AB and we slid it across to A double prime, B double prime. Okay, so that's what this theorem is saying. Okay, couple of other things though that are really important. A double prime, so this line right here is perpendicular to these parallel lines. And we know that from before. When we have a reflection, you have to remember that it's perpendicular. The line of reflection is not the line of reflection, but the line that goes from the image to the pre-image is perpendicular, just like we have here. Okay, and this is new. This is important. Okay, because this is going to be used in the homework and later on in the lesson. A to A double prime equals 2D, where D is the distance between K and M. Okay, so we've got our parallel lines. This distance right here, if we take this distance, that's twice the distance from here to here. Okay? All right, so let that kind of sink in for a minute. And we will go on to the next one in the next video.